Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we'll get started. It's great having Thomas here from CMU. Thomas is a professor of computer science, and he has affiliate appointments in the machine learning department at CMU, as well as the program in algorithms, combinatorics, and optimization. And he's also part of the newish CMU UPIT joint PhD program in computational biology. And I've known Thomas for a number of years. He's been working in areas of interest to both of us, that are dear to my heart and soul, in bounded rationality, decision theory, game theory, some of the core challenges we face in AI when we have limited resources and information. He developed, per the topic today, some leading algorithms for several general classes of game. And these algorithms we'll hear more about today won the most recent world championships in computer heads-up no-limit Texas Hold'em. They also have lots of interesting implications for other kinds of problem-solving in machine intelligence more broadly. Thomas did his PhD work at UMass Amherst, working with mutual colleague Victor Lesser for a number of years before coming out to CMU. He probably remembers on his way to becoming a professor, stopping off at Microsoft Research, where Jack Breeze and I worked very hard, including a boat trip in a rainstorm. I hope it's a different jacket you're wearing today.
I was actually thinking it's exactly the same looking jacket, but I swear it's a different jacket.
we tried to convince Thomas to come to MSR as a full-time researcher back then, and I think he actually considered us seriously. Rainstorm to the side, but literally he was dressed like this in a pouring rainstorm on a boat in the middle of Lake Washington, and he was very good-spirited about it. In 2003, Thomas won the Computers in Thought Award, given out by the Ichkai folks. He's a fellow of ACM, AAAI, and Informs. And he's published, I've often reflected with some colleagues that Thomas is like a publishing giant in terms of the breadth and depth of his publications in several different areas of work. And beyond that, he's managed to start and sell a very interesting startup, run it over a number of years, help on the boards of other kinds of startups and venture-oriented entrepreneurial projects. He has algorithms running in the real world, including, I think, a very interesting set of procedures that are now being used in kidney exchanges. And he came here about 3 or 4 years ago and just gave a talk on that work, which I think has such incredible societal benefit. So with that, come on up.
Okay. Thanks a lot for the very kind introduction. And thanks a lot all for coming here. So I was asked to talk about kind of the state of the art in solving poker. I wanted to generalize that a little bit out into games beyond poker and kind of the technology capability that the community has built over the last 10 years, which is a huge leap. So 10 years ago, there was this kind of perception that, hey, don't work on game theory, it can only solve toy problems. Well, that's no longer true. And I couldn't help myself but put some new content in here as well, so it's not just an overview talk. So if you have heard all of my talks in the past, there's about 30% new material here. All right, and this is a joint work with a number of PhD students and collaborators, and I'll show those names on the slides as we go to each piece. Okay, so the game formalism that we'll be using is going to be the absolute standard extensive form incomplete information game, which is this. So there's a game tree much like in chess, except that there are these white nodes which represent nature's moves. So you can model nature as a random player that moves stochastically, not strategically, and has some probabilities for their actions. And also there are information sets which represent incomplete information. So for example, when the red player is in this state or this state, he doesn't know which one of those two states he's in. So he knows that he's in one or the other, but doesn't know which. And similarly, the blue player doesn't know which one of these nodes he's in when it's his turn to move. Any questions on that formalism? Okay. What's a strategy here? Well, it's a mapping from information sets to actions. So it will say for the red player, which action would you take here? Which action would you take in this information set? Which action would you take in this information set? And so forth. The strategy can be probabilistic. So it might say, okay, here you go 40% here, 60% here. And clearly the strategy should depend on where you believe you are in the information set. So for example, the blue guy might want to do a different thing here and here, but he can't because he doesn't know where he is, but he can actually derive beliefs as to what's the probability that he's here versus here. And once you have the strategies, you can just use Bayes' rule to derive the probabilities. Okay. Come on in, there's plenty of seats. Don't be shy.
You won't sign us.
Okay. I'm going to be talking about domain-independent techniques. The application area is logically going to be poker, but there's nothing poker-specific here. Techniques for complete information games like chess or checkers don't apply here, so you have to have completely different techniques. Challenges here include unknown state, uncertainty about what the others and nature will do, and in my opinion, most importantly, interpreting the signals that the other players send. So when the other players take actions, it signals to me about their private information. And conversely, whenever I take actions, it signals to the other guy about my private information. And how do I take those into account? Well, the beauty about Nash equilibrium, which is a solution concept by John Nash from 1950, is that it gives a solid definition on how those signals prescriptively should be taken into account. But of course, the Nash equilibrium solution concept is just a definition. To operationalize it, you have to have algorithms for computing Nash equilibria or approximations thereof. All right, so Nash equilibrium is a strategy for each player and beliefs for each player so that no agent benefits from using a different strategy. So no agent unilaterally can benefit from deviating. And this is the solution concept that we'll be using throughout the talk. In one place, I'm going to talk about the refinement as well, and I'll just make it clear. Okay, most real-world games are actually like this. By this, I mean incomplete information games that fit into the general extensive form game model. So negotiation, auctions of various forms, military things, cybersecurity. So like we've done some work on wireless jamming games, and I have some ideas how to do operating system security applications of that as well. Medical treatment planning. This is something that I'm super excited about. We have a new big grant proposal pending on that, where you think about the world as there being a treater that treats a patient and a disease, two players zero-sum game. For some nodes of the game, you have some probabilistic information that's good. For other nodes, you don't. So you have this kind of mixed stochastic versus game theoretic situation. And then you can use game-solving techniques and opponent exploitation techniques for making sequential treatment plans. And biological opponents furthermore have the limitation that they can't look ahead. They have like one-step look ahead, and you can actually exploit that as well. So we're actually, with a biology collaborator, proposing to use this for steering the adaptation of the T cell population in an individual, so as to drive their own T cells to battle cancer or to battle autoimmune hepatitis. And if we get the funding, we'll actually be doing wet lab with in vitro and then in vivo in mice. All right, enough of that. Oh, by the way, thank you, Microsoft. We got a little seed grant to get that work started a couple of years ago. Okay, poker. Well, that's a benchmark. I don't really view it as an application, although you can view it as such, but I view it as a benchmark. And it's a challenge problem in the AI community since about 1992. There's hidden information, which is the other player's cards, uncertainty about future events, deceptive strategies are needed in a good player, so you can't always play the good hands aggressively and the bad hands weakly, because the opponent will pick up on that and do very, very bad things to you. The game trees are very large. I'll talk about how large. And some of the techniques I'm going to be talking about here apply to general sum multiplayer games, and some apply to just two-player zero-sum games. And if it's just for two-player zero-sum, I'll mention that on the slides. I should mention that two-player poker is a zero-sum game, and it's actually a very popular form of poker. So it's not like we just looked at that, because that's the only thing we can look at, which is also true. But it's high stakes. Some of it on TV, but most of it is actually online. So real nosebleed level, high stakes play, two-player, mano a mano. A lot of professional gamblers prefer that form. And so it's very interesting, and they are super good, unbelievably good at that. How quickly they can adapt, how sophisticated their strategies are. Some of these people are without college degrees, yet they are so smart. It's just unbelievable, kind of humbling. All right. So here's our approach, which is basically now used by all the leading poker research groups. This was foreshadowed, of course, by other things. So the idea of automated abstraction was already here, but then there wasn't custom equilibrium finding and manual abstraction and so forth. But here's the idea. You have the original game, and in the case of two-player, or in other words, heads-up, no-limit Texas Hold'em, the number of information sets in the game is about 10 to the 161. So bigger than the number of atoms in the universe, but even if you had, for every universe, you had a sub-universe and counted those atoms, it would still be less than this number. So it's a big game, you can't write it down. We run some automated abstraction algorithm that takes as input some compact representation of the game. Think about a rule sheet printed on one piece of paper, if you will, to an abstracted game that is similar, or hopefully similar, we'll talk about that, to the original game. Then you run a custom equilibrium finding algorithm to find a Nash equilibrium of that abstract game, and then you use a reverse model or reverse mapping to map it back to an approximate Nash equilibrium of the original game. Any questions on this framework?
Can you just explain on abstraction a little bit more?
No, I can't explain it a little bit more because I have like 30 slides on it, so I'm going to say a lot more about it. Yeah, I'll talk about it in detail now. Okay, so lossless abstraction, which almost sounds like an oxymoron. It's more like finding isomorphisms, if you will. The observation there is that we can make games smaller by filtering information a player receives. So for example, instead of observing a specific signal exactly, a player instead observes a filtered set of signals. So for example, if the player is receiving an ace of hearts, we'll say, okay, he received an ace. And sometimes some of the other detail doesn't matter. So this form of abstraction is just merging information sets. So there are two information sets that the player can distinguish between. We're going to say, okay, now he can't. In the abstract game, he can't. And if we do it losslessly, we only remove redundant or irrelevant information from that model. Does that answer the question? Yeah.
So Thomas, has it been helpful, and do we know what kind of abstractions human experts use?
Okay. So this has been very helpful. I'll talk about that on the next slide. We don't really know what abstractions humans use.
So this suggests you're not going for a flash, right? So.
I'm not. This is an example. I'm not saying that you can ever actually pull this abstraction off in a lossless way. This is an example of what this might be. And we are not programming in the abstractions. We generated this algorithm called GameShrink, which automatically identifies all of the abstractions like this and makes them. So we don't have to know in advance what kind of abstraction you could actually do and still be lossless. The algorithm will smell them out itself.
But in many information sets, this abstraction should work, shouldn't it?
Yeah, well, I'm not going to argue this particular one, but I'll argue another one which is easy to understand. So let's say that you get your first two cards in Texas Hold'em. Whether it's an ace, let's say you get two kings. King of hearts, king of spades versus king of hearts, king of clubs. Same thing at that point. They only become important later when the flush considerations so become relevant. And that's captured. So if you bundle something, it doesn't mean that you're going to bundle it forever.
by that, do you mean that you're encoding some like symmetry information of the game priorly? Like
No, you're not encoding it. You're algorithmically identifying it.
putting it like in your set of candidate abstractions that can be considered as, say, homomorphisms.
I'm with you except for the putting it in part. So it's actually considering all of them itself. Okay. So we're not putting in candidates. It's figuring them all out.
I guess there are 29 more slides coming, so we can maybe.
Well, 29 on this, and that's the first topic of many. Okay, so with this, we solved a game called Rhode Island Hold'em Poker, which was an AI challenge problem introduced by Xi and Littman to be kind of bigger than the Coon poker that John Nash solved in the 50s, which was, by the way, the only game in his thesis. So the connection between poker and game theory actually goes way back. And smaller than Texas Hold'em, because it was viewed that Texas Hold'em is so big that we can't ever make real traction on it. That actually turned out to be wrong. But anyway, 3 billion nodes in the game tree. Without abstraction, the sequence form linear program, which can be used for equilibrium finding, has 90 million rows and columns, so it's unsolvable. GameShrink, which is our abstraction algorithm, ran in 1 second and collapsed the game down to 1% of its original size. 99% of the game was actually irrelevant. So after that, the LP had 1.2 million rows and columns, and at that point, with the best LP solver, which was the C-plex barrier method, it took 8 days on a small supercomputer in my lab, and we could just crank out the exact answer. So we solved the exact Nash equilibrium in this, and that was the largest incomplete information game solved by over 4 orders of magnitude at the time. So that really showed the power of abstraction.
Thomas, when you say solve, you're solving an abstract version of the game.
But a lossless. So this is a Nash equilibrium of the original game.
So you prove losslessness.
You prove the GameShrink algorithm proves losslessness, and so it finds the exact Nash equilibrium, and not close, but all the way to machine precision.
You said the word "the." Of course, in general, we know there can be multiple.
Yeah, I meant to say N. That's right. There could be multiple Nash equilibria. Yeah, and this found one.
Of course, some could be better than others. You have a way to.
Oh no, they couldn't. So in two-player zero-sum games, you have a nice swapping property that if you play any one of the Nash equilibrium strategies, and the opponent plays any one of his, they all pair up equally well against you. You get the same values. Yeah. Okay. So sometimes, though, even though lossless abstraction gets you in poker about 99% of the game to go away, if you leave 1% of 10 to the 160, that's still a big number. So in Texas Hold'em, you have to do lossless abstraction to get anywhere. So now I'm going to talk about first the leading practical approaches and the history of that, and then some new theory about how do you tie abstraction to the Nash equilibrium quality in the original game. So I'm not going to, in the interest of time, talk about everything, but from 2007 to 2013, the main ideas for practical abstraction were the following. One was integer programming to decide how many children each node at the level gets to have, because you don't want to have a uniform abstraction. Your computing resources for Nash equilibrium finding tell you how large the abstraction can be, and you want to use that size smartly where it matters. Secondly, potential aware, I'll talk about that, and then imperfect recall. Imperfect recall is the idea that you may want to forget something that you knew in the past in order to make your abstraction smaller and buy yourself more space to refine the present more finely. That used to be kind of a weird notion in game theory. There were just these obscure things, but now it's actually a very practical tool in solving games. So now I'm going to jump to the currently best abstraction algorithm, which combines the ideas of potential aware and imperfect recall and earth mover's distance, and then it obviates the need for integer programming. All right, and I'm going to do kind of a transformation from how that literature went. So first, expected hand strength is the goodness of your hand, assuming that nature and the opponent rolls out cards uniformly from then on. And early poker abstractions used that as the measure for clustering hands, clustering the information that the players get. But that doesn't really work that well. So here's an example where you have expected hand strength being basically equal, but the hands are very different in the middle of the game. So let's say we've started with 2 pair of 4s, or we started with 10 jack suited. Very different hands, both have expected hand strength 0.57. So your algorithm might bucket those together, or they should be played completely differently. And why are they different? Well, this hand is pretty much usually mediocre. Pretty good, not great. If you get the triple, yeah, that's great. But it has very little mass here, and it has a lot of mass here. This is the opposite. It has quite a bit of mass here and no mass here. So basically, this hand is going to end up really good or terrible. Okay, so those should be played differently, and that can be captured in distribution-aware abstraction. So you look at the full distribution of hand strength, basically the histogram on the previous slide, and then you use, for example, earth mover's distance as a distance metric between the histograms. It turns out earth mover's distance is much better than L1 or L2. Come on in, don't be shy. Do you want to open the door? I guess they're being shy. Yeah.
Go back to the last slide.
Yeah.
Yes. So, you said that these expected hand strengths are interpreted as sort of like a value function. Is that right? Or
yeah, I guess you could call it a value function. Yeah, but it's not really a value function because it's not based on the strateginess or what the player and the others are going to do from then on. It's assuming a uniform rollout.
Yes. But what if they imagine that the opponents are going to roll out in a strategic and adversarial way?
Right.
Will the clustering criteria according to that, like expected hand strength, be perfect or at least better?
No, I'm saying that even if they don't do that, it's going to be imperfect. Now I'm doing this kind of transformation into better and better things. Okay. So before the 2014 paper, the prior best approach used this distribution-aware abstraction with imperfect recall. But that doesn't really take the potential into account. And potential is something you read about in the poker literature, but nobody's really been able to define it. So we actually define it operationally using kind of a recursive formulation. And let me show you an example of this first. So let's say we have 2 situations. This is the game with private signal x1. This is the game with private signal x2. Here, with probability 1, you get no information in the next step, and the uncertainty resolves in the second step. Here, the uncertainty resolves in the first step, and you get no more information in the second step. They have the same distribution to the last round, but very different potential. And what we do then, instead of thinking of transitions to the last round histograms, we think about transitions to the next round histograms, where the base of the histogram is the states of the next round, which we have already abstracted by moving bottom up in the game tree to do the abstractions. Did this make sense? You're not so sure?
Say it one more time.
Okay. The algorithm starts from the bottom of the game, from the leaves. There's no potential left there. So we can use your favorite metric, like expected hand strength, to cluster those. Now you have clusters there. At the previous level, now you can look at what is a probability distribution of transitions into those next level clusters. And of course, the earth mover distance now is in a multi-D space. We cluster based on that, and that's how we move up the game. And again, we can use imperfect recall throughout. So
The earlier versions just looked at the final state only.
the earlier ones, these ones kind of looked at the transition from a current state to the final state histogram. And now we're looking at the transition level by level, or step by step in the game. But that also means that you don't have this type of x-axis. You have this multi-dimensional thing where you have to do the earth mover's distance. So we do that, and we developed a custom algorithm for that, to approximate it because the normal Earth mover algorithms don't scale. And this led to the best abstractions evaluated experimentally.
So one would think, stopping for a second, that you'd be losing information with that abstraction step, that particular one.
Yeah, all of the abstractions I'm now talking about are lossy. You have to lose information, otherwise the game ends up being too big.
As you go on, you're talking about lossy abstraction.
Yeah, the first.
I can imagine come back to say there's no loss later.
No.
I'm gonna. So the thread on this part of the talk is gonna be: we started with lossless, gets rid of 99%. That's not enough. Have to abstract more. Here's the practical stuff. And then we're going to talk about theory that actually gives you bounds, that even if you abstract in this way, you're still bounded with respect to the original game. Yeah.
And
That's a thread here. I'm not there yet.
And Michael Bowen's work also did similar kinds of bounding.
Yeah, I'm talking about not only our work, but throughout this, like here, this was Michael Bowling's group. This was Alberta group before Michael Bowling joined. Michael Bowling's work. Yeah. So I'm trying to do a little bit of a overview of the field, not just a presentation of our. Okay, so Tartanian 7 was a program that won the most recent annual computer poker competition in the no-limit heads-up category, and it uses an abstraction similar to what I was just talking about, except in a distributed way. So we can run on clusters now, or we were running on a cache-coherent, non-uniform memory access supercomputer for that competition. And the abstraction just uses any favorite abstraction algorithm like the one from the previous slide at the top of the game. You can define top any way you want. We defined it to be the flop round in poker. Actually, sorry, pre-flop. And then the rest of the game is split into equal-sized disjoint pieces based on public signals. So you can put different computers working on the different pieces. And it's important that you do it based on the public signals, because that guarantees that the information sets don't cut across computers. All right. And how do you do that? Well, you have a base abstraction generated with the algorithm on the previous slide, and you can look to transitions into that to have a well-defined algorithm. And then for equilibrium finding, we used external sampling Monte Carlo counterfactual regret minimization, or a variant of that, which is from University of Alberta. It starts at the top of the tree, and then when it gets to the rest part, it passes samples a flop from each public cluster, and then you continue the iteration on a separate plate for each public cluster, and then you return the nodes. There's some details as to how do you actually make it work in this distributed context we could talk about that you have to do, otherwise it won't converge. And then you can do multiple samples into one of those continuations if you're worried about the communication overhead, so it becomes minor. Okay, now to Eric's bounds.
Just an idea of how much time does this?
As much as you can give it. So as many cores as you can give it, as much time as you can give it. We were running, this spring we were running, this is the previous spring, about 1,000 cores for about 3 months. We'd like to take it to an order or two more cores in the future, yeah.
Maybe a technical detail, but are you maintaining your belief state at each node in the tree? Or you have some particle like sample representation of that?
The beliefs are maintained explicitly. So for each information set in the abstraction, for each action, CFR maintains the probability and one number for the regret. Yeah.
So I'm a little confused. So you run this thing for 3 months, and then you have a representation that you can play any game? Is the idea that with no further computation, or this is so
No.
particular instance of one game?
Good question. So this is, if we go back to that framework slide, so it starts by getting the description of a particular game. Then the abstraction algorithm is run on that description, spits out the abstraction for that game, and then the equilibrium is computed for that game. So the algorithm is general, but the run is specific to that game, to that input. Not even all poker. Heads up, no limit Texas Hold'em poker. Yeah.
Okay, but so you have a solution for that particular poker game that you can now take to a tournament and
Yes.
run in real time.
Right.
And how big is that representation?
I don't remember how big it was here. For the next program that we developed this spring, which is Claudico, it was 1.4 terabytes.
And it's a big table of...
Big table. 1.4 terabyte table of action probabilities.
And does it ever make sense as the game evolves to just try to get ahead of it with real-time computation?
Yes, I'm gonna get to that. You're so smart, you know. You should tape your mouth because you're jumping me ahead. Okay, good. So lossy game abstraction with bounds. This is actually tricky due to a known fact in games, which is called abstraction pathology or abstraction non-monotonicity. Again, from the University of Alberta here. Basically, in single-agent settings, be it in planning or MDPs, what have you, if you make an abstraction that's finer-grained, your solution quality can't go down. In games, that's not true. You come up with a finer-grained abstraction, even if it's a strict refinement of your original abstraction, your solution quality can actually go down. So it's for a while, that kind of threw the whole framework into in question. That if that's true, why are we coming up with these finer and finer abstractions? Maybe we're actually taking steps backward. But then we started looking at lossy game abstraction with bounds, first for stochastic games, and then for general extensive form games, and I'll show you a few results on that in the next couple of slides. The abstraction is performed in the game tree, not in what's called the game of ordered signals and the signal tree representation. So these are now general purpose, unlike the game shrink algorithm, which was for that game of ordered signals class of games. It's for both action and state abstraction. So we so far talked about state abstraction, where you bucket the information that you get, but you can also do action abstraction, which is really important in games with large or continuous action spaces. You choose some of the actions as the action prototypes and pretend that the rest of the actions don't exist. We'll talk about that in detail. And here's a detail. More general abstraction operations are enabled here by allowing not only many-to-one mappings of the states, but also the other way around, one-to-many mappings, and you can get some leverage from that. Okay, so here's the main theorem. And this is joint work with my student Christian Kroer. For any Nash equilibrium in the abstract game, any undivided lifted strategy is an epsilon Nash equilibrium in the original game, where epsilon is defined like this. So what is an undivided lifted strategy? Well, lifted strategy just is something that works in the original game in the obvious way you would think about. And undivided is a constraint on how we reverse map. So it's not a restriction on games, it's just a constraint on how we reverse map the answer back to the original game. And now what is this? This is the kind of where the action is. It's looking at measurable things in the difference between the abstraction and the real game, and then tying it into the epsilon in the epsilon Nash equilibrium, which is a game theoretic notion. Okay, so what is this? 2 times epsilon r. This is a utility error, and this is defined recursively. At the leaves, it's just the error between the model, the abstraction, and the actual game. At interior nodes, if it's a player node, it's a max of what the players can do. And if it's a nature node, it's just a probability-weighted sum of what nature can do. And you maximize over agents, and you maximize over information sets, and that gives you this value. Then there's maximum over players of the sum of the heights where it's player i's turn to move of epsilon j0 times this w. This is a nature distribution error at that height. So how wrong is your nature model at worst compared to the real game? And you add that to the sum over heights where it's nature's turn to move, 2 times this epsilon times this w, where this is the heights of the nature turns and nature distribution error at height j, and w is the maximum utility of a player in the abstract game. So that, I didn't expect that we'd walk through the proof or anything, but this gives you a very concrete thing that where you can measure everything on the right-hand side by just looking at the abstraction and looking at the game, and then it ties it to saying that, okay, if you abstract it this way and solve the abstraction, your error in the original game in Nash equilibrium is at most epsilon. Yeah.
So you mentioned previously that when we get finer abstractions, the actual solution can actually like go worse, right?
Yeah,
And
but yeah. Oh.
I guess the hope is that with these transition and reward error bounds, you would hope that the upper bound will behave in a better way, but actually we know that they don't. Right?
Ah, good question. Not quite, but somebody's being eagle-eyed here. That's good. So how is it possible that I'm giving you a theorem that says that as I'm getting closer in the abstraction, finer grained in the abstraction to the original game, my epsilon is going down, and I just told you that it's well known that there are abstraction pathologies where it actually goes up. What gives? Exactly. This is a bound, and it leaves some room for non-monotonicity as we are approaching the real game with abstraction. All right. So the utility error side of the bound is tight. The nature distribution error bound is tight up to a factor of 6. Hardness results, well, determining whether two subtrees are what's called extensive form game tree isomorphic is actually graph isomorphism complete. This is something that you need to check even for lossless abstraction. And it is not obvious because the graphs have special structure, so you might think that this might be easier than graph isomorphism, but it's not. So this says that it's hard. Computing the minimum size abstraction given a bound is NP complete, and the other way around as well. Minimizing the bound giving a maximum size of the abstraction is NP complete. So now you might ask that, wait a second. As a preprocessor, you're solving some NP complete problem, and then you're doing the equilibrium finding, which in two-player zero-sum is actually polynomial time. How does that make sense? But these are, of course, worst-case results, and in practice, it's not only helpful, it's necessary to do the abstraction. And you don't have to do it optimally. Okay, this is just showing an impossibility of level-by-level abstraction that shows that you have to actually consider the whole tree, or at least you can't focus your attention on level by level as all of the prior abstraction algorithms have done if you want to have bounds. Even if you want to have lossless abstraction, you can't do that. But in the interest of time, let me not walk through that example. Okay, extensions to imperfect recall. So that theorem was for perfect recall. We have extensions to imperfect recall as well. And there's a paper from Alberta by Langtot et al. Here we get exponentially stronger bounds than that. And we get bounds for a broader class of games where abstraction can actually introduce nature error as well, which is somehow something that they precluded from consideration. And furthermore, our theorem is for any game. Theirs is just for the counterfactual, any equilibrium finding algorithm. Theirs is just for the counterfactual regret minimization algorithm. Okay, so now, as I thought about this abstraction theorem, it actually brought up an interesting other connection, which is if you think about modeling, models are never the real world. Modeling is a form of abstraction. And typically in game theory, when we take the model and solve it, we actually take the answer as if that's somehow applicable to the real world. But we had no connection that says that how does the answer actually relate to the real game. Now these are the first results that actually tie that gap as well, if you can measure the gap between your model and the reality, or at least bound it. Okay, action abstraction typically has been done manually and still oftentimes manual. There's been some automation. Again, this is from a different group from University of Alberta. For stochastic games, the theory we had applies, the theory that I just talked about applies. And then with my PhD student Noam Brown, we developed the first algorithm for parameter optimization for one player in two-player zero-sum games, where you can actually have one player control some parameter, like, for example, the bet size. And then as you change the bet size, you don't have to restart the whole equilibrium finding. You can warm start with some really clever stuff that Noam did here. And that allows you to move bet sizes, and you can actually move multiple bet sizes at once. And as long as the payouts are convex in the bet size vector, this is actually guaranteed to converge. But I'm going to show you something cooler later today, so I'm going to skip that part. All right, so that gives us, that's all I was going to say about automated abstraction for now. Next is custom equilibrium finding. How do you solve the abstract game? And now I'm going to really look at two-player zero-sum only. Okay, this is kind of giving a perspective on the field. On the x-axis we have year. On y-axis we have on log scale the number of nodes in the game tree that had been actually solved or near optimally solved. And you can see that when the annual computer poker competition was announced around here, it really spurred a lot of interest in this. And people started building on each other's work, and we saw this super exponential jump in the technology capability. I'll talk about this, the best algorithms in detail in a little bit. Now, especially when you're in the CFR family, you want to measure complexity not in the number of nodes, but in the number of information sets. So here's a newer graph that I made. Again, years on the x-axis, number of information sets on a log scale on the y-axis. And you can see that this exponential growth has continued to this day. So you can actually solve games now with about, what is that? 6, 12, 13, 10 to the 13, or a little bit more than 10 to the 13 nodes in the game tree. And I don't have that number for this one, but for this one, the number of nodes was already 5 times 10 to the 15.
So it's interesting when people, I often get questions, is our advances in AI, how much are our advances due to power of machines getting better and more memory getting cheaper? And I often say, well, it's really going to come down to innovation in the problem-solving space, and it's going to bust out of the kind of constraints that we see as the power of the computation. Of course, you need some. So you can imagine plotting Moore's law against this graph, have it sort of seeing it really level out scale here, and go flat while the AI innovation is created.
That's right. This is almost all algorithmic innovation, right? Or AI innovation. I like that term. Yeah.
These dramatic improvements, you're exploiting the structure of the problem, right? So if I come up with a new game of Texas Hold'em and I'm going to add
I wouldn't say that. I wouldn't say that.
Vacuous integer on that card, I can say that my search tree has exploded dramatically because I have more information. But because it's independent of the game, I can just decide to ignore it.
Oh, yeah. This is not the size of the original game. This is the size of the abstraction. So now, if you go back to this picture, so this was 10 to the 160. Keep that, 10 to the 161. Here, we're measuring how much comes into here. What is the size of the abstract game that gets fed into the equilibrium finding algorithm? That's what's on the y-axis now.
I wonder if you could actually, a cool graph would be also the bound. There's some notion of a bound on the optimality on this graph here.
Bound on the optimality in the real game.
Right, as a function of the size.
Yeah, for limit Texas Hold'em, there's been some of that. And this, I actually know the answer for this. It's 1 milli big blind per hand. So it's so close to optimal that a human playing for a lifetime at human speed could not tell with statistical significance whether they're winning or losing, even if they're playing optimally. Milli big blinds per hand, so 1,000th of a big blind. So for this, it's known. For this is for no limit, and no bounds are known for no limit, because you cannot even run the best response computation, so you can't even ex post check how close to optimal you are in no limit. So it's a whole different beast. Okay. Best equilibrium finding algorithms, counterfactual regret from Alberta.
Sorry, back to the last slide.
Yeah.
So, but if you use the same algorithms going back down on the size of the abstraction, you'd be interested to just understand as a function of constraints on the richness of representation, what the error is. The current best algorithm would just put some constraints on sort of maybe the actual nature or the size or richness of the abstraction.
Yeah. So how this went is that the practice went way ahead of the theory, as usual, many years before the theory. So the theory is relatively new, and we haven't actually tried to tie the theory to any one of these things, the abstraction algorithms that were used before you got to these numbers. So that hasn't been done. But what's been done in limit Texas Hold'em, you can actually expose compute the best response and measure how exploitable in the original game you are. And so I know the answer for that guy. Okay, best algorithms, well, counterfactual regret from Alberta, scalable EGT from my group, completely different algorithms. So it's amazing that completely different algorithms and they have selective superiority, which is kind of weird. This is based on no regret learning. This is based on Nesterov's excessive gap technique. Most powerful innovations here, well, the number one is that each information set has its own separate no regret learner. If you think about doing no regret learning in the whole strategy space, you're totally dead in the water. It's way too big. But here, you can actually isolate it to each information set separately, which is a brilliant innovation. And sampling. You can actually sample the tree over and over at each iteration, so you don't have to walk through the whole tree. Here, most powerful innovations, well, first of all, smoothing functions for the excessive gap technique that satisfy the conditions of that technique for sequential games that enable this idea to be used for sequential games in the first place. More aggressive smoothing. Helps by an order of magnitude and still satisfies the constraint. Balanced smoothing between the primal and dual, also kind of an order of magnitude there. And then you can get memory scalability by taking the memory to a square root of the original if the actions don't depend on chance, which is the case in poker. So fortunately, this can take your memory to a square root of the original. This iteration complexity is 1 over epsilon, and each iteration is slow. Here, both of these parallelize. Here, the iteration complexity is much worse, 1 over epsilon squared, but each iteration is fast. So these are totally different. So you think about this doing billions and billions of iterations to solve, each iteration running in less than a second. Here, each iteration is like a day, and maybe you do 200 iterations. So totally different in that sense as well. Selective superiority, so one can be faster than the other depending on the game and the abstraction. One thing that's nice about this is that you can run it on imperfect recall abstractions, although it's not guaranteed to converge to an equilibrium, but at least you can run it. For a while, this couldn't even be run on that, so we kind of abandoned this for a while. Also, with some condition numbers on the matrix, you can get log 1 over epsilon, which is the best possible. So that's the same as in interior point techniques, but interior point techniques aren't scalable for memory. All right, one slide on a new paper here. So a new prox function for the first order methods such as excessive gap technique and mirror prox gives the first explicit convergence rate bounds for general zero-sum extensive form games without requiring the condition number, the log 1 over epsilon. So you're getting this complexity, but much faster and for much more general setting than our original paper.
So Thomas, while the slide is up, I was going to ask you, just reflect like maybe 30 seconds on how this kind of semi-parallel pursuit at Alberta was influencing your team in terms of learnings or directions or contrast to what the Alberta team was doing.
Okay, great.
Over the years.
Over the years. So abstraction, we've certainly been building on each other's work a lot. On the equilibrium finding, we went in the exact opposite directions. So this is coming from kind of a machine learning, no regret learning tradition. We came from the optimization tradition. When these had very little interplay, except that when imperfect recall became the abstraction of choice, we had to abandon this because it didn't do imperfect recall. This one, at least, although it doesn't have any guarantees, you can run it. You can press the button and see what happens. And that actually ended up being the best approach for a while. And then, because of that, we actually went and said, okay, can we improve this? And for the last couple of years, we've mostly been coming up with better and better things here. So now we've been building on that. And now the next slide I'm going to show is actually an improvement on this thread. So now we're actually pursuing parallel threads. in my group, this thread and that thread. And here there's a lot of interplay with and building up on each other's work with the Alberta group. And other groups. It's not just us and Alberta, although they're the leading groups, but the Eric Jackson from California, Tim Reif from California, Oskari Tammelin from Finland. There's a Czechoslovakian group that's very strong, French group that's very strong. So there's been a lot of building on each other's work. Yeah. Okay. So new prox function, better prox function for these optimization-based techniques. That introduces gradient sampling schemes. So in particular, it enables a stochastic first-order approach with convergence guarantees for extensive form games. So now you can start to do sampling. We did some game sampling before, but now you can actually do gradient sampling in this optimization framework as well, which was one of the big reasons we moved away into the kind of no-regret space. And it introduces a first-order method for imperfect recall abstractions, which is the second reason we moved away from that. So now I would say that both threads are alive again. Okay. It's a kind of a weird post-processing deal. Actually, let me skip that. Endgame solving, and coming back to your real-time question. So far I talked about the game being solved up front, huge strategy vector, and then just look up at a runtime. But you can actually do endgame solving, and this has been very powerful in complete information games like chess. In fact, for solving checkers, that was the whole thing. It was a big dynamic program that was the whole game as the endgame, and that allowed Jonathan Schafer to solve checkers. In imperfect information games, endgame solving is totally different due to the information sets. So benefits, first of all, finer-grained information and action abstraction, because you're in a specific context, you can afford to do finer-grained. And you can dynamically select the coarseness of your action abstraction based on the size of your endgame. And this is actually something that threw the humans off really badly in the man-machine brains versus AI match that I organized this spring, in that humans usually think a lot when there's a lot of money in the pot in no-limit Texas Hold'em. This does the opposite. If there's little money in the pot, the end game is actually bigger because there's more races that are possible still. So it actually has to think more. So the smaller the pot was, the more the computer thought, and that really rubbed the humans the wrong way. Anyway, new information abstraction algorithms that take into account the relevant distribution of the players' type distributions and types entering the endgame. So by the time we get to the endgame, we can use Bayes' rule from what's been played so far, get the distributions, and we can now decide where we need more resolution in the abstraction versus not. We can compute exact equilibrium strategies rather than approximate ones, because now we have a much smaller game. We can use LP instead of these iterative methods. We can compute equilibrium refinement and solving the off-tree problem. So if we've action abstracted before, we have been rounding back into the abstraction what the opponent has done. And our model, our thinking of where we are in the game in terms of pot size might be off. So now we can start again. We can start with a real pot size and fix that problem right on that spot.
And all the solutions are made to fit in the tractability of what's considered a normal response time?
Exactly. That's exactly right. And you can control the coarseness of the abstraction to accomplish exactly that. All right.
But I guess comfortably? Or is it the idea that if you had a little bit more time, you could do a lot, you give a sense for the actual profile you're on?
Yeah, we do have a little, I don't have a graph on that, but you can develop that sense very easily as to what the trade-off is. And one of the trade-offs we did in the man-machine is that we said that, okay, we don't want to take more than 20 seconds on the last betting round, because that's something that is quicker than what humans on average do, and quicker than the pros did on average. But it's still kind of annoying. If you think about it, each pro gave 2 days of their life waiting for the computer to respond over 2 weeks. So we felt that 20 seconds was the right number. If we had, say, 2 minutes, we could have had a much more refined endgame abstraction and played better regarding card removal and things like that the pros actually picked up on. But it's with the same algorithm, just giving it a finer-grained abstraction.
I wanted to get back to this question earlier and ask if it relates to always having, always starting every hand with the same pot size, with the same chip stacks.
Yes. So if you wanted to, the game with different chip stacks is a different game. We'd go through the whole loop again.
Right.
That's right.
So in that would be an example that would be an example of the issue that you raised earlier, because you would, in essence, have to recompute the entire. You have to compute many different games.
Yeah, and people have done that. So if you want to play a poker game where you have different stacks as a starting stacks in different hands, and people have done that. We've always focused on the annual computer poker competition style, where it's always the same chip stacks to start out with, and that's how we played with the humans as well. And that's how when we. Yeah, let me leave it at that. Yeah. Okay. It's not perfect though. So think about rock, scissors, paper. If we are in this yellow endgame, where the first guy has moved 1/3, 1/3, 1/3, here we can conclude that, because he's moving randomly 1/3, 1/3, 1/3, might as well always move rock. The endgame solver could conclude that playing rock always is just fine. And of course, that's a disaster. So it does have its perils, and we have some theory that ties the size of the end game to the rest of the game, but that's kind of largely an open research question. How do you tie the end game solving into the game so that it's not very exploitable? Alberta has also done some work on that, and they have some guarantees, but in practice, our method seems to be doing better than theirs, so it remains to be open how that can be done in a semi-safe way at least, and still practically playing well. Okay, experimentally, it helps. We did a test in 2012 in No Limit against all of the top players. Tartanian 5 was our bot then, and adding the endgame solver improved performance against all of the competitors, including itself. And then you can also look at removing weakly dominated strategies first and looking at equilibria on the remaining set, which is a refinement of Nash equilibrium, and that helped even more. And this you can solve with LP, this you can solve with 2 LPs. You're done. Okay, here's another idea that Sam Ganzfried, my student, came up with. The idea was that what if we knew some domain knowledge about the game that we're solving? And now we're, by the way, in limit Texas Hold'em, not No Limit. Maybe we're right, maybe we're wrong, but we have some gut feeling that there's some regions in the end game. So for example, as we go stronger hand, weaker hand, in this region, we should bet fold. Here we should check call, and so forth. And this is what the opponent should do. We have some gut feel that that's how it's going to be. We've seen humans play like that, or we're making a guess. Turns out that now we can write an integer program that will actually find an equilibrium that matches this qualitative structure if it exists. And the idea is that so basically the integer program is trying to place these cutoff thresholds in the right places. And the leverage that allows us to do the integer program is that at a threshold, I have to be indifferent between doing this and doing that. That's the short of it. And you can actually make multiple guesses, and you can test each one of them. And if you're right, you're getting the Nash equilibrium. And that really speeds up endgame solving if you want to use this idea. And also, it allows to sometimes prove existence of equilibrium in games where it hasn't been proven or couldn't be proven before, and solve games for which no algorithms existed, including multiplayer games. Of course, you have to have the guess. And the good thing is that you can be wrong about it. And if you're wrong about it, the integer program is going to tell you, you're an idiot.
So when you say existence of equilibrium, what is the setting?
Let me, in the interest of time, take that offline. It's kind of a long story. That's not poker. They're weird kind of continuous games that don't fit Nash's original theorem. Okay, so we talked about that, custom equilibrium finding reverse model. So the reverse model is this problem. Let's say that we have a continuous action space or a large action space, and we have the red action prototypes. The opponent could play outside of those actions. What do you do? Of course, you can yourself decide to play into those, so you never fully get yourself off track, but the opponent you can't control. So let's say F of x is a probability we map to the down, and 1 minus f is probability we map up. We came up with this axiomatic approach. What would be good desiderata about f? And of course, you might want to have more, but these seem to be at least what you want. So if you're at A, map to A. If you're at B, map to B. Monotonicity, as you get closer to B, the probability of going to B shouldn't go down. Scale invariance, whether you're playing for $1 or $100, the reverse mapping should be the same. Small change in x shouldn't lead to a large change in f, and small changes in A or B shouldn't lead to a large change in f. And here's an answer. The pseudo-harmonic mapping that we put together actually satisfies these desiderata. It's derived from the Nash equilibrium of simplified no-limit poker, and it's much less exploitable than prior mappings in simplified domains where we can evaluate it, and it performs well in practice in no-limit Texas Hold'em. In particular, it significantly outperforms the randomized geometric mapping, which did the geometric average and randomized according to that. All right. Now comes something that I couldn't help putting in because I'm so excited about this. This is not an overview part. This is kind of the bleeding edge of what we're doing, or one of the bleeding edges of what we're doing. Joint work with my student Noam Brown. And the idea is that action abstraction we talked about could have a large or infinite branching factor. We pick the prototypes, let's say those 3. But the opponent can move out. We have to map back. All right? Problems? Well, it's a chicken and egg, really. How you should abstract depends on the equilibrium, because you should abstract things together that are played similarly. But you can't start your equilibrium finding before you have the abstraction. If the abstraction changes, you'd have to start the equilibrium finding from scratch. Kind of sucks. Abstraction size must be tuned to the available runtime. So if I know that, okay, this spring I have 1,000 cores with 3 months, based on my practice experience in the past, I know that this is roughly the abstraction size. But what if somebody donated us another month of computing or another 9 months of computing? Then we would have wasted our time running on a coarser abstraction that we could have used. Finer abstractions are not always better, as we talked about, and can't feasibly calculate exploitability in the full game in large games like No Limit. So the new idea is this. Instead of going through the old sequence, we are going to collapse all of that into one. We call it simultaneous abstraction and equilibrium finding. Okay, so how it works. Let's say we have the original game like that. Again, blue player, red player. We want to add this extra action for the blue player. The idea is that we assume the action was always there, but was never played according to the counterfactual regret algorithm. So now this is actually tying to the counterfactual regret algorithm that we talked about. 2 challenges. What happened in that branch on iterations 1 through t that we really didn't run on that branch because it wasn't really there? And this may violate the CFR algorithm, so the regret bounds might not apply. Now we're going to solve those. The first thing is that we're going to fill in the iterations. We're going to generate this thing called the auxiliary game, where we're going to put all of this the rest of it, which we had already computed, into a special node, kind of an outside option that the player can take, or the player can go into this new piece. And then we're going to compute CFR in just this game, which is much smaller. And furthermore, you don't have to compute all t iterations of it, because you wouldn't actually have reached this node on all iterations of CFR. You can just weight it based on the reach. So this kind of fills in what happened in those iterations. All right? And then we copy the strategy back here, and voila, we can continue. One fly in the ointment is that in imperfect information games, an action may originate from multiple information sets. But we can solve that by putting an extra chance node in there, and it plays according to the same probability it was reached in the t iterations in CFR. Okay. An alternative to the auxiliary game is called regret transfer, something that Noam again put together. And it doesn't always work. It works for special cases where the payoffs are a function of some theta, which is the action. Poker typically has this flavor where you can say, okay, now I'm going to raise the stakes by a factor of 3. So then you have an identical structure to another subgame in this new subgame. We're going to store the regret as a function of theta, and when adding a new action, theta 2, we copy over the regret function and replace theta 1 with theta 2. This runs in constant time, so we can in constant time add this instead of the order t time which the auxiliary game required. Okay, now regret discounting applies to both the auxiliary game and the regret transfer. As I mentioned, the second problem was that if the new action was never played, we may have violated the CFR execution and the regret bounds don't hold. So we have to fix this. And we can do this by de-weighting the old iterations. So 0 means that we give them no weight, 1 means we give them full weight, and we have this theorem that says that how much weight can you give them and still satisfy the CFR regret bound. And these are all measurable quantities that you've already computed. Eric, you look unhappy or puzzled.
Unhappy. I was just thinking about the question, which is this. Maybe you can answer it. And maybe you can just say it's a natural equilibrium, so don't worry about this. Is if you had two machines playing each other, doing this with knowledge of each other, are you still in a world where you can assume, I just don't, I was trying to sort of entail what that would mean at the level of a reflective policy, knowing about this algorithm on both sides.
Okay, so the short answer is that I'll have to take that offline. I'm going to think about that. I'll have to think about that. That's a good question, because the way I'm thinking about this now, and we have with Noam been thinking about this now, it's an algorithm that you run before any play happens. But another thing that I want to do is that as I see the pros, be they human or computer, play some actions that are out of my abstraction, I want to throw them in my abstraction and do this somehow online.
But I guess I don't know if all your assumptions hold in that situation.
I think they do, because I'm just ignoring what the other guys are actually thinking. I'm just going to... And one thing that I'm thinking here is that I'm going to let them play out of the abstraction and not do this if, according to best response, they're actually shooting themselves in the foot. So we could actually know that the human pros that we were playing this spring, some of their manipulations were actually hurting them. So we just let it go. And then those ones that actually hurt us, we throw those back in the abstraction.
So one interesting thing to see that's similar to this is not just play the human pros, but give them a copy of this where they can express their beliefs of what hand they think the computer holds. Run the algorithm and say, if I knew what the computer was holding according to my beliefs, what would the algorithm do in this situation, and how do they change their behavior and response? So in other words, they still don't know what the computer's doing, but they're able to simulate the computer given their own beliefs about what the computer holds. So I put you on an ace-king, unsuited. What would you play in this situation? I can actually run the algorithm and see what you'd play, and I can adapt now to how I think you play.
Okay, interesting. I'll have to think about that. Okay, good. And it's not always best to go all the way to the least de-weighting. Here's something that worked well in practice and satisfies the theorem. And again, these are things that you've already computed. So no extra effort there. And where and when to add actions? Well, we talked about doing this online, where based on what the humans do, but we can actually do this automatically offline. You'd want to add to the abstraction actions that are exploitative in the original game. One way to do it is to compute a full game best response and see which ones exploit. So the idea that we did in the experiments is that we add an actions when the derivative of the average regret with respect to time is more negative with the action than without it. Here's a formula for it. Let's not go into the details on that. The key here is that we can add any number of actions at once, and one action can be at multiple information sets and add it like that. So you don't have to just add piece by piece. And also you can, of course, start from some manual abstraction and then add top of that. You can also have stronger conditions to be more conservative about what you add, and the theory still goes through. The claim is that, and obvious actually, eventually this will add every action that has omega t regret growth, which guarantees convergence to an equilibrium in the original unabstracted game. So it will also avoid the abstraction pathology. All right, full game best response, that's kind of a subroutine here. Actually, let me skip that, because that's kind of a detail. Removing actions. Some actions may be added early but turn out to be useless, so we can also remove them so they don't keep dragging our computation down. In two-player zero-sum games, if an action is not part of a best response to a Nash equilibrium strategy, then the regret goes down to minus infinity, and the action needs to only be explored in CFR for a constant number of iterations in the beginning. This could be a large constant, but still a constant. And furthermore, some of these iterations can be skipped. The idea here is that we can project, if we do negative regret, how many times would I have to hit that part of the game in CFR to get to zero regret? And only then would that start to get revisited. So I can already project that I can skip so many iterations and I don't have to go to that subtree in those iterations. Experiments, well, we tested on continuous Leduc Hold'em. Leduc Hold'em is one of the standard benchmarks in the field. Continuous just means that we have continuous actions. The initial abstraction contains just a minimum and maximum bet sizes, so we're not putting any handcrafted information in. And we are testing against fixed abstractions with branching factors 2, 3, and 5, which are placed not just uniformly, but smartly using the pseudo-harmonic mapping. And here's what we have for the benchmarks. So if you look at here, full game exploitability, as we compute more, exploitability goes down. And the smaller the abstraction, the quicker it converges in the beginning, but then it ends up higher and doesn't go so well in the long run, as you would expect. Now we put our stuff on here, and you can see that we actually do better than the small abstractions and better than the large abstractions. So it really accomplishes what you wanted, and it reaches zero, while any fixed abstraction that's not the full game will actually cap out and not reach zero. And in fact, it will overfit into the abstraction and start going up in the end. Okay, so let me just skip that. Okay, so now we could talk about, I have two more pieces here. One is opponent exploitation, and then is actual how is the state of poker. I can get both of them in within the 90 minutes, or we can skip one or the other in the interest of time.
We might want to leave some time for questions or some discussion, so why don't you just pick?
Okay, I'm going to try to zoom through both then. More is more.
I thought I was implying one or the other, but it's okay. Or is also mathematically inclusive. Or so.
Okay, well, I'll skip this part then. I'll skip this part, and I'll just tell what it is. So one is a hybrid between playing equilibrium and using opponent exploitation. So the machine learning techniques for opponent exploitation have been tried in poker, and they really can't hold a candle to the game theoretic stuff. But the game theoretic stuff doesn't fully exploit the opponents. So we have a paper that hybridizes those, start from the game theory stuff, and as we get more and more evidence that the opponent is making mistakes, we adjust our strategy to exploit. And the second paper I was going to cover is what we call safe exploitation. So if you start to deviate from equilibrium, from all equilibria, so you're playing something that's not part of any equilibrium, you can exploit the opponent more, but you can open yourself for counter-exploitation. And the folk wisdom was that that's kind of an inherent problem you can't get around from it. But now we can actually ask, is it really true? Or can we exploit more than any game theoretic strategy would and still be completely safe ourselves? And the answer is, surprisingly, you can. And why? Well, what you do, you can't, the high-level idea is this, and the first part is wrong. So you would like to bankroll your further exploitation by the winnings you've made so far. But you can't quite do that, because if you mock with your upside, you still have the full downside, and your expected value becomes negative, becomes below your actual game value. So what you do, you tease out the role of luck from the role of mistakes the opponent could have made and given you money. You measure this, or at least lower bound this part of what your opponent gave you due to mistakes, and that is the amount with which you can bankroll your exploitation into the future and still be fully safe. That's it. So now let's move to poker. So that trade-off doesn't start at zero. State of poker. And this is the fun part. Oh, I guess it depends who you are. How many of you play poker? Okay, great. State of poker. So as I mentioned, in Rhode Island Hold'em, 3.1 billion nodes in the game tree, exactly solved. Key was a lossless abstraction. standard LP solver. So nothing fancy in the equilibrium finding side. Heads-up limit Texas Hold'em. The bots surpassed the pros in 2008. University of Alberta organized a man-machine match against 2 pros in 2007, lost it. 2008 they did it again and won it. So in 2008, in limit Texas Hold'em, which has 10 to the 14 nodes in the game tree, information sets in the game tree, both surpassed humans, and now it's what the Alberta guys called essentially solved. So it's solved within a very close bound to optimal, 1 milli big blind per hand. And what was key here, this was a new variant of CFR. They used the standard lossless abstraction methodology. They actually hard-coded it in as suit isomorphisms to pre-process, and then they used a new variant of CFR for that. Heads-up no limit, 10 to the 161 information sets, much bigger, a whole other kind of worms. You can't even measure currently exploitability, how close to optimal you are. Tartanian 7 won the annual computer poker competition, so that's our bot. What we did then for the next few months, we made an even better bot called called Claudico. And then I organized this man-machine match where I got 4 of the top 10 pros in the world in heads-up no limit Texas Hold'em specifically to come and play 80,000 hands of heads-up no limit Texas Hold'em at the casino in Pittsburgh. And each one was playing alone against Claudico. And here are the 4 pros: Jason Les, Doug Polk, Bjorn Lee, Dong Kim. And here's a supercomputer we use to compute the Nash equilibrium. It's a blacklight supercomputer. And here's our team, so Noam Brown and Sam Ganzfried, who are my PhD students. All right.
Okay, how to get this.
What?
Okay, how to get display sitting there. You need something sitting there, right?
Say again?
So like they get having a display sitting there.
Oh, I know. I didn't. I thought that was funny. They actually made a custom heads-up table and all of these things, and then they made like a chair, had a chair, and like there's something there, but there's nothing there. I thought the casino did a fantastic job with the setting. It was just awesome. We actually were doing duplicate poker to reduce the role of variance. So 2 of them were actually playing in public, and with the reverse cards, another pair of them were playing in a private room with armed guards upstairs. So there was no cheating. And we tried to really reduce the role of luck here to try to get statistical significance, but we failed. So 80,000 hands, although that's right at the upper limit of what the humans could do in terms of their time. Still not enough. So the humans won more chips than the computer, but it was so close that we couldn't get our 95% statistical significance to say who's better. But oh well.
These are highly rated pros.
Yeah, these are 4 of the top 10 pros in the world. Doug Polk considered number 1. He came number 2 against the computer. Bjorn Lee actually came in as number 1, won twice as much as Doug against the computer. Dong, oftentimes considered number 2 or 3 in the world, barely beat the computer, and Jason Les lost to the computer. So these guys carried the day.
It really is impressive looking at the methods to think about what on earth humans are doing.
Oh my goodness. And oh my goodness. And these guys don't have the game theory vocabulary. I mean, he has a math and economics bachelor's from University of Chicago, and he's a computer science bachelor's. No college degree. I don't think a college degree. And he was drawing graphs to me about the endgame, where the y-axis is a defense probability, and the x-axis has this thing, and he had these curves, and it's spot on. Like if I had to teach that stuff, I could take this guy's graphs, and the guy doesn't have a college degree. It's so amazing. And when we...
But even the idea that the obvious noisy abstractions they must be using are getting so close to beating you.
Or they are beating us.
Yeah.
So
something you said about whatever these abstractions are, and then plus and minus all the noise and all the craziness. Without theorems and proofs.
Yeah, unbelievable. And somebody might say, hey, well, they played a lot of poker. They've read books and played a lot of poker. Wait a second. We play more poker in self-play on the supercomputer every spring than mankind has ever played. So, okay, anyway.
It's just a reflection.
Yeah, it is very impressive. And also when we changed our bots, like on some days we were turning the in-game solver on versus off, so it would actually have different flavors. We would change the pseudo-harmonic mapping, whether we'd randomize it or not, you know, to give, try to throw curveballs at these guys. Within 150 hands, they picked up on everything. It's just unbelievable. Anyway, this is what it looked like. This is all on Twitch and YouTube. You can look at all of the hands. This is really like a university for poker if you want to study this. You can look at 2 weeks of poker. This is
A comment about Microsoft. Peter, you want to say a couple words about why our name appears up there?
Well, in the state of Pennsylvania, in order for this to be legal, there needs to be real cash, prize money put up, and so we, MSR, provided the cash awards for.
yeah. So we had the pros need to get paid to do this, and we couldn't gamble for real money. The Pennsylvania Gaming Board didn't allow that. And in hindsight, it's probably a good thing. CMU would have lost part of its endowment, I guess. So generously, Microsoft sponsored half the prize, and the Reverse Casino in Pittsburgh sponsored half the prize. And in addition, we had the Pittsburgh Supercomputing Center. They were sponsoring the supercomputing. AI Journal was sponsoring the laptops, and so forth. So thank you. It wouldn't have been possible without you. I mean, quite literally, we were like 2 weeks before, and before the commitments were hard, you know, the casino would not have run this event if it hadn't happened.
It was, for some reason, our purchasing department had a hard time issuing a purchase order. It took a while.
So I had, yeah, thank you. Okay, so these pros took it very seriously. The 2 weeks of poker, 1 day break, and these guys, these are not the kind of cigar smoking, scotch drinking, Stetson hat wearing guy, all American guy. No, these are like international pros who study all the time, and they have computational tools. They flew in a guy from Florida to help them do the computational analysis during the day, and during nights they were doing computational analysis. We allowed them to do anything.
Well, I guess you're saying that one day there might be human versus machine where there's no support, right?
Yeah, we allowed them to have support.
Yeah.
Yeah, well, you know,
Except for your computer.
What?
Except access to your computer.
Except access to our. So we gave them the logs every night so they could analyze that. And so they had all of the tools. They could use computers. So they were kind of a human-computer hybrid, if you will. But they took it very seriously. So they're stretching here in the morning. They were eating oatmeal at the casino for breakfast. I saw them drink 1 glass of red wine during those 2 weeks, and I hoped that it would jinx their team, but I guess not. Okay, multiplayer poker, well, bots aren't very strong. In special cases, like programs for Jamfold tournaments, we've solved it near optimally, but by and large, it's not even clear that the Nash equilibrium is the right thing to play there. And there's some really interesting results from University of Alberta for 3-player Coon poker. Even there, you know, what strategy I pick, I can't really help myself or hurt myself, but I can allocate the money between Max and Eric radically differently. So Max wants it, yeah. So it's not even clear that Nash is the right thing. Then what can we learn from bots? So how do humans learn poker? Well, they read books and they play poker. And who wrote the books? Well, humans. And it's kind of a recursive thing, so it kind of falls on itself. There's no ground truth there. In contrast, the bots, they're working from the definition of the game only and the definition of Nash equilibrium, so they're sitting on ground truth. And the bots actually learn to play very different kinds of strategies than the humans have evolved to play. So problem is that the bot strategy is a big probability vector, 1.4 terabytes in the case of Claudico, of probabilities. So it's hard for a human to understand stuff from there. But I'll mention a few things that it does differently. So first action to limp. So limping in poker is that when it's your move, you're the first mover, typically you want to raise or fold. Limping means that you just call. It's like, okay, I'll play that put. Considered a weak move. And so here's what this book says about it, poker book. Limping is for losers. This is the most important fundamental in poker for every game, for every tournament, every stake. If you're the first player to voluntarily commit chips to the pot, open for a raise. Limping is inevitably a losing play. If you see a person at the table limping, you can be fairly sure he is a bad player. Bottom line, if your hand is worth playing, it is worth raising. Similarly, Daniel Cates, who's one of the other top 10 players, not one of the ones in the tournaments, he verifies that in two-player heads-up, no limit, limping is a bad idea. Well, our bot limps. And it's not just this bot. Every bot we've computed for this game has always limped, between 8 and 12% of the time. So that's an indication that limping might not be a bad idea. And in fact, the name Claudico is Latin for I limp. We named it after its signature move. All right, donk bet. A common sequence in the first betting round is that the first mover raises, the second mover calls. First mover is representing strength, second mover is not. The latter has to move first in the second betting round by the rules. If he bets, that is called donk bet or donkey bet or bad player bet. Like if you represented that you're weak and now you're representing you're strong, something's rotten in Denmark. You're not really that credible. So considered a bad move, our bot donk bets. And with various sizes as well.
There's a Latin word for donkey in there somewhere.
By the way, when watching it, when you witness that, you as a human, you're sure you misremembered.
Oh yeah, you can start to doubt yourself. You, as a human, you're like, whoa, that was so weird. Now I must have misremembered, but there's actually a string there that encodes the whole hand history, so we gave that to the humans as well. So we didn't try to take advantage of the humans' bad memory. Not that they have a bad memory, they can remember these hand sequences from days ago in full detail. But if a layman like me plays, it's nice to have that sequence there. It's okay. No, I actually didn't remember. He didn't misremember. He did make that donk bet. Okay. Using more than one bet size in a given situation risks signaling too much. Remember we talked about the signaling. Most pros use one bet size, some use two, and this is a little bit of an old bullet. Nowadays, pros have started to vary. Some pros have started to vary the bet size a little more. Our bot uses a wide range of bet sizes, randomizes across them, and what the human said is perfectly balanced. So it will bluff and it will value bet in the same type of situation with the same types of bet sizes, including huge ones and tiny ones. So it would make a 10% bet on the river to open, or it would go all in on top of 1/40 of the pot. Sorry, it's 40 times the pot or 37 times the pot and so forth. All right, conclusions. Domain-independent techniques, combination of abstraction, equilibrium finding, reverse mapping, and then opponent exploitation. Claudico, we turned the opponent exploitation off completely, so Claudico never actually saw how the humans played poker. So we just did it in a purely game theoretic way. Let me leave it at that.
So can you say why?
Why? The opponent exploitation techniques really risk a lot, depending on the technique, because they're not safe, except the one that is safe, but it doesn't exploit much either. So we thought that was a risk. We thought that there's very little to exploit in these top pros. So we just didn't go there. For the next time, I have my own ideas as to what we're going to do. We're going to do some of that in a very different way than we've done in the literature so far.
That's an assumption that's important to test because if maybe there is something still to exploit.
Yeah, maybe there is something. I'm sure that there's something to exploit. The top players, they say that, okay, I believe that there's a lot to be exploited. It's just hard to find those exploitations in a reasonable number of hands before you've lost a whole bunch of money trying. One thing that suggests that there is a lot to exploit is that the human poker play in no-limit Texas Hold'em has changed quite radically over the last 10 years. So it was actually kind of a soft game 10 years ago, and if you put in a half a year of study, you could actually make a lot of money. That's not the case anymore. Nowadays, the top pros are very good, and they're randomizing, and they're using these notions of balance, card removal, very sophisticated things, and they're learning from each other. They actually have these schools. So Doug Polk is actually the trainer of two of these other pros, so Dong and Jason. because he's so scared. People are so scared of him online. He doesn't get any action. He's so good that nobody wants to play him. So what he does, he takes these younger guys he calls students, just like professors. He calls them students that he trains, who come in with a no name and will play not as quite as well as him maybe, but really well using his strategies, and they will get action until they become too famous and nobody wants to play them either. But that is how the ecosystem works. Thank you.
We've had good discussion along the way, and it's already noon, so if there's a burning question, we'll take it. But otherwise, thanks everybody. Great, thanks.
Thank you.